2, properties of the normal distribution. The normal distribution. Many quantities are distributed symmetrically and unimodally about the mean in a bell-shaped curve. This distribution is known as the normal distribution. A population that follows the normal distribution can be described using two parameters: the mean, mu, as a measure of central tendency, and the standard deviation, sigma, used to describe the spread of data. So, if we're measuring some random variable, it's likely that it fits the most common type of distribution where it's centered around the mean and is symmetrical. So, the properties of normally distributed data. For any normal distribution x, 68% of the data is within one standard deviation of the mean, approximately 95% of the data is within two standard deviations of the mean, and approximately 99.7% of the data is within three standard deviations of the mean. So what can we take from this? That regardless of the kurtosis or the shape of that bell curve, this one's a little bit wider, this one's a little bit skinnier, regardless of the variable that we're measuring, typically we have the same amount of data within a certain standard deviation of the mean. So what we can do is use a standard model to talk about the to be able to approximate any random variable, and we call this the standard normal distribution. The probability density function is given by this equation. Now this is the equation for the top curve of this function, but as mentioned before, in order to get the probability of an event, we need the area underneath the curve. So instead of using a formula to calculate that area underneath the curve, we will be using a ZScore table, which we'll be discussing shortly. So the values have already been calculated, we just need to be able to use this table. So integral calculus is needed to calculate the area underneath the curve to approximate probabilities. The standard normal curve is normally distributed with mu equal to 0 and the standard deviation set to 1. Normal probabilities can be approximated using a z-score, and this is the z-score. Your particular observation, x minus mu, that's referred to as x minus mu, is a deviation, divided by the standard deviation. And that will tell you the proportion of standard deviations a particular value is from the middle. So it describes how far a point is from the middle in terms of a standard deviation. A z-score table in our textbook is page 606. I'll include a separate digital copy of this table because you'll use it frequently anytime you're using the standard normal distribution. This is used to approximate probability under the curve to the left of a particular z-score value. So if you had a positive z-score like this, it will take the area underneath the curve to the left-hand side. Let's say that this was the value 1.12. So the probability z is less than 1.12. The way that we'll use the table on page 606 is the following. There are columns and rows. So rows and columns. This will give you precision to the nearest tenth because that's 1 unit after the decimal. And then for 1.12, we have 1.1. This would be 1.10, 1.11, 1.12. If you're tracing the top columns, you'll notice that this is adding precision to the nearest hundredth. So the probability that the z-score is less than 1.12, so the area to the left-hand side of that z-score, is 0.8686. So again, this is a table that is designed to be able to calculate area underneath the curve instead of using a formula to calculate that area. So let's look at some scenarios. Predictions from a normal model. Less than the probability that x is less than or equal to a particular value. So this is one case. All that glitters, a sparkly cosmetic powder, is machine packaged in a process that puts approximately 50 grams of powder in each package. The actual masses have a normal distribution with mean 50.5 and standard deviation 0.6. So it's important to note that the random variable being measured, the masses, are normally distributed, meaning that it has that bell-shaped curve for the random variable x, which measures mass in grams. Its mean is 50.5 in the middle, and the standard deviation is 0.6. That's the average distance from the middle. So the manufacturers want to ensure that each package contains at least 49.5 grams of powder. What percent of packages do not contain this much powder? So we're looking for the probability that it's less than this value. We were given these two values, the mean and standard deviation, which means our z-score, if we look at the difference between x and mu and divide by the standard deviation, we get negative 1.67. That is our z-score. It is 1.67 standard deviations to the left-hand side. And we want to know the probability that our z-score is less than this. So we are approximating this value using the standard normal curve. Notice that this is the distribution with the variable being x, but we can approximate this, and I'm going to say the following. We're approximating this value using the z-score. So the z-score table is the curve, the standard normal curve, which has the mean as 0 and the standard deviation as 1. So this is an approximation using that curve. And this is similar to the area underneath that curve when the z-score is negative 1.67. So the area underneath the curve to the left of negative 1.67 using this curve. So we'll have to use the z-score table in order to accomplish that. So I'm going to pull up the z-score table here. Our score was negative 1.67. Notice that in our textbook there's two pages, this page and this page. The only difference, these are positive values, these are negative values. And what we're going to do is look at negative 1.6. One moment. Negative 1.6, that's as close as we can get to the nearest tenth, but then we need to add precision to the nearest hundredth. Negative 1.67, notice that that is happening from these columns. So we look at that intersection. I'm in the 700th, sorry. 1.67 is here, 0.0475. And that is our best approximation for the probability that a package contains less than 49.5 grams of powder. Similarly, I'm just going to talk briefly about the strategy for each of these different techniques here. This is the scenario when you have the probability that x is greater than a particular value. And what we will do is, if this is our value, we're looking to the right-hand side. Remember that our approximations using z-score tables are to the left-hand side of that value. So in order to calculate the area to the right-hand side, what you can do is look at the total area underneath the curve, and that's equal to 1. And the part that we want to get rid of, this is like the indirect method because we're going to exclude the component that we do not want. 1 minus the probability that x is less than 168, so the total, 1, minus this component will give us the area that is greater than that point. And that's the strategy that is used for areas underneath a curve to the right of a particular value. Lastly, if there's an interval, we're looking for the space in between 2 points. What we can do then, if areas are measuring always to the left-hand side, what we can do is take the right endpoint. So we're looking here at the left endpoint, right endpoint. We want the area underneath the curve in an interval. And what we can do is take the area to the left of the right interval, so that's all of this area underneath the curve, take away the area underneath the curve to the left of the left endpoint, x1, and the remainder is the difference between the two. So notice x2 refers to this point here, x1 refers to that left endpoint here. And that strategy will help you find areas underneath the curve in an interval.